Hello everyone, I am Kartik and I am going to present work done by Tao Zhu et al. Which was published in CVPR 2018. It's titled AttnGAN, Fine-Grained Text-to-Image Generation with Attentional Generative Adversarial Networks. So let's start off by first defining the problem, which is text to image. As you would expect, the input is a textual description. It can be something like an image caption or some kind of description which basically tells you about the components of the image. The output is an image, which is usually RGB. So when you see this caption, we as humans are naturally gifted with this capability of imagination. When you see this sentence, you are able to visualize a scene without ever actually having to see that precise scene, and that is what we want our models to do. So given this as input, we want to generate something like this, and as you would have guessed, there are more than one correct answers to this problem. So this is what we want our model to learn. Even generating any one of these images is fine. We'll now go through the related work to see how this line of research has progressed and get the general idea of how they are approaching this problem. So the first paper in this line of work is this, done by Scott Reed et al., published in ICML 2016. So this is the gist of their architecture. They have an RNN encoder which they concatenate with the noise vector and basically pass it on to the generator. This is our normal generative adversarial setting which we know. Next is an improvement done by the same group in which they have additional input information such as bounding box information, key point information to tell the network where the actual object is located in order to generate it. So this gives the generator more information and hence should be better in principle. Next up we have AttnGAN. So they proposed a multi-stage generation process, which is what we will be looking into in AttnGAN as well. But the main idea here is the generation process is done in multiple stages. So you have one generator here, another generator here, and their corresponding discriminators. This was done by Zhang et al. And then the same group provided some minor improvements to the original model in which they interleave those generator networks. But that's about it. That's the minor improvement. Those are the minor improvements they make. Next up, we have plug-and-play generative networks. Their original task at hand was not text to image, but one of their settings does actually solve it, in which they have this recurrent this loop wherein the generated image would be passed on to an image captioning network, and they'll basically try to closely align the generated caption to the actual description so that you have an idea that this is indeed the image that was described. Next, we move on to our architecture, AttnGAN's architecture. But first, before looking at the architecture, we would like to look at the motivations they had to come up with such an architecture. So the first point here is, as we have seen so far, that this T2I or text-to-image problem looks like an encoder-decoder problem. You feed in the text from this direction, and the decoder is basically decoding it to an image. But they want to turn this into a sequence-to-sequence problem. That's no problem for the text part, because LSTM do sequentially process this, but you have to sequentially process the image generation as well, do it sequentially as well. So this was first seen in AttnGAN, and we'll see it here as well. So the image generation here is an M stage process, not a single stage, M stage. So you would have M different generators and their corresponding discriminators to generate a final image. Next, the idea to convert this was, the motivation to convert this into a sequence-to-sequence problem was because in recent year, in actually last year itself, there has been many developments in the sequence-to-sequence model, example attention. So you want to sort of leverage these kind of improvements in this line of research. So that was the motivation. They also do text-to-image alignment or verification whether the actual, after generating the image, whether the text and image do actually match to each other. So they propose a component in the final loss as well, so which we'll talk about. So these are the 4 motivations for coming up with this architecture. So this looks pretty complicated at first glance, so let's we'll go through it part by part. So let's first start with the where the input goes in. So we'll begin with the text encoder, where you have your input caption, which is a T-word sentence, which has basically T words, and the text encoder is a usual bidirectional LSTM, which has hidden states for forward direction as well as backward direction, and you concatenate them to get one hidden state per time step. Then the sentence feature is actually the final hidden state, and it has a dimension of D. So it is denoted by E bar. So a general notation that this paper follows is wherever you see bar on top of a variable, that is representing the global thing. So it would be like for a complete sentence or a complete image. Whereas if you have word features, those would not have a bar on top of them. So just keep that in mind when you see variables. So now coming to the word features part. Word features gathers hidden states from all time steps. So if you have a T word sentence, this will basically be T. That's the only difference. So you stack them all up column wise and you get this E matrix. Next step, we go to the conditioning augmentation. This conditioning augmentation actually has the effect of randomly sampling variables, latent variables from a Gaussian distribution. So your E bar, which is received as input to this stage, is first split into mu and gamma. You can do this by just a simple fully connected linear layer, and then you use the first half of that as mu and the second half as sigma, whichever way you like. So you use those mu's and sigmas here and you combine them with a noise. So this is sort of like the formulation you have for the middle section of a variational autoencoder, where you have another noise vector. They basically add this additional noise vector here to have higher variation in generated images for even a single caption. So even if you have a single caption, your mu and sigmas are known, but this part leads to a final different code output, which can give you a different result, different generated image. So they want that, and that is what they do. So next up, we have this code C vector concatenated with the Z noise vector. This is just a standard input you have for generative networks as a noise vector. So you have this concatenated input and you use this in the further stages, which we'll talk about. Okay, so we have covered this much. Now we will go to the generator, which is the zeroth state generator, F network. So this one, as you can see from the legends here in the diagram, that you first have the fully connected with reshape, and this network is basically responsible for most of the upsampling. So you finally get an output which is this of this dimension, and your upsampling blocks, each of them, they are done using nearest neighbor interpolation, and the scale factor is 2. So every upsampling block, you double the height and the width in each of these upsampling blocks. So as you can see, the upsampling actually all of the upsampling is done here. So here the output would be 64 cross 64 cross some number of channels, which we'll deal with later, but basically the height and width for the generated image in this stage has been achieved. So this first stage does not actually use any word level features. The word level features that we extracted over here, they are not used. We are in this first stage, we just want to use the sentence level features, and which is what we give as input to this F0 network.
So is this a vector or is an array, is an image output?
Okay, this is supposed to be a 3D volume. They reshape it to have this final N for the subregion so that you can process it more effectively in the attention part. They do reshape it for the con layer. So moving on, this is the attention model, which is basically the heart of the paper. So we'll look into it, how it takes this H or the context vector at this stage and gives you word context or region context vector, as we'll see later on. So this attention model, let's get into it. So this does the role of combining word features, which is E, combining that with the previous stage context, so I-1. So this first F1 takes H0 as input and you combine them. How do we combine them? There's a 3-4 step process which we'll look into now. They first bring the word features to a common space. So this is the dimension, working dimension for the words as we saw previously, and this is the network's internal working dimension. So they try to bring everything to this dimension. And that is what they do here. This is just a linear fully connected layer. Next, you combine this with context. So this modified E, which is E prime, you use that over here, and you have this core, which is basically combined with the context. So as you can see here, this is the simplest form of global attention that they have used, just the dot product. There are other ways of doing it, but this is the easiest one, which does not require any parameterization over here. So that is your S prime. Next.
Sij, can you say Ij what?
Oh yeah. So as you see, Hj at a Hj here indicates one sub-region of the image. So for jth sub-region and for the ith word, you would have this score. So you have this for all of them, and that is how you go on. You use this score for each of the individual. So there's a combination, like this word with this sub-region, this word with this sub-region, and each one of them will have this score, S prime. Next, we use that to generate a word context vector. So a way to intuitively understand this word context vector is, for one sub-region, you're looking at all the words. It is global, since it is global attention, you're looking at all the words, and you're selecting which one is important for generating or painting this particular sub-region. So this is the formulation for that. Let's first go into the beta variables here. This is just a softmax kind of function for this score we just calculated, and this combined with the modified word features gives us word context vector for just one region. So you see, one region sees all the words, as you can see from the summation here. So you have this word context for all the regions. So you repeat this entire process for each region, and that is basically the output of your attention network, as you can see over here. This again has the working dimension of this network's internal dimension times the number of sub-regions the images have. Okay, let's move on. Let's move on to the next stage of the generator. This one again is also responsible for the upsampling. So as you can see here, the first layer, this one actually receives two vectors as input, the output of the attention, all the word context vectors which we just obtained, and the context, the direct context vector H0, which we had as output from the previous generator stage. So you have both of them as input. The first is just the joining here, as you can see. These are residual blocks which actually don't change the height or width. They are designed that way they are used just to make the network deeper. And then you have just one upsampling block. So here the height and width would effectively be 128 by 128 across some number of channels. That's it. So the upsampling here is the same as before, nearest neighbor interpolation, twice the scale. The resonant block, as I said, does not change the height and width. And yeah, so this one does use word level features, because that is what the output was from the attention network, as you can see here, and it takes the previous state's context vector output. So you have this general formulation for all I from 1 to m-1, which means basically this is the same structure that is followed in all the generators from here on. We'll go through that as well, but this is the general structure that the following generators follow. Okay, let's get on further down in the pipeline and see the next attention network. So as you would expect, it has the same structure as the first attention network. Instead of H0 it obviously uses H1 as input from this current generator's output, and that's about it. There's literally nothing different. Then finally we have our final generator, which has the same structure as F1 and uses H1 as input along with F2 ADTN's output as input. So one thing you would have noticed here, since this is designed in such a generalizable way, you could have gone even further, and in principle you could have gotten even higher resolution images, but the authors pointed out that they stopped because of the GPU consideration. But in principle you can have, let's say, another generator attached here and have 1024 or go up till the original image resolution. That's it. Now let's look at the generators. So each of these F generators have their corresponding G generators as well, and they have the exact same structure. So we'll look at all of them in one go. And here it is. So since you noticed that, you would have noticed that the upsampling has already been done, you only need this one convolution block, which is a 3x3 convolution, to reduce the final number of channels to 3, so that you can visualize this as an RGB image. And that is what it basically does. It takes the context vector from the current stage and gives you x hat I, which is the predictor or the generated image. For this particular one, a single layer configuration, you have filter size 3, padding 1, so it does not change the height or width, which we don't want it to, and stride 1. Yeah. So now let's talk about a bit about the losses. So these generators, each of them have their individual losses. So LGI, you would have a separate loss for each of these generators, and we do that and not just the loss for the final generator, because we want each one of those generators to learn something meaningful and not have the burden of learning all on the last generator, let's say. So you use all of their losses, and we'll talk about what this exact term stands for, but basically we sum those up to get the generator loss. We'll get back to the final loss later. Okay, since we are talking about generators, let's talk about discriminators and how they are designed. So these are the 3 discriminators, as you can see, attached right after the generated image. And as you would see from the diagram here, they do take this, this green line means just taking this code or the sentence level features and not the noise vector, which may be confusing to some. It was to me. So this green line you see here just takes the sentence feature, and we'll talk about that how. So the discriminator has 2 forms, unconditional and conditional. So the unconditional is the usual discriminator which we see in adversarial settings, which has the job of classifying the image as real or fake from the real distribution or the generated distribution. In addition to that, we also have a conditional form of the discriminator, which says whether the image and caption are of the same pair. Notice that it isn't actually learning that the caption and images are same. It is just pointing out the fact that they are of the same pair or not. There's a subtle difference here, which basically means if you have an image and you have that caption fed in, the caption of that image, this discriminator should output something close to 1, ideally 1. And if you pick just some other caption from the data set, just some random caption, and fed it with this image, it should output a value close to 0. So these are the binary kind of questions, the 2 binary questions that those discriminators are trying to answer. So let's look at the adversarial loss for G. This G, the first part is the unconditional loss, wherein it will try to bring, these are the generated images sampled from this generator or the distribution that it assumes to be. And you would pass that to the discriminator. So now since you are trying to minimize the loss, it will try to bring this close to 1, and as we'll see, the discriminator is trying to do the opposite. It tries to bring this close to 1 so that the discriminator is sufficiently fooled and your loss is minimized. So this is LGI's unconditional part of the loss. We also have the conditional one where you'll notice the only difference is passing this E bar along with the predicted or generated image to the discriminator. So this is answering the second question, and this is answering the first question over here. And that's it. That's the final loss for LGI, and this is the same thing that follows for generators at each stage. Next up, we have cross entropy loss for discriminators. So this has 4 parts. The first part is, since the discriminator sees data from the original distribution as well, it will try to bring that close to 1, whilst it will try to minimize the output of the, it will try to minimize basically the generated images output and make it close to 0, so that the discriminator loss is minimized. So this is the unconditional part for the entire thing, for the discriminator, and this is the Yeah, and this is the first part of the conditional loss, so I can't take my pointer down there, otherwise that thing bugs me. So we have this additional input, just this additional input as you can see, and the same thing follows over here as well. So you have that as part of the conditional loss. So that's it for the LDI. This is not used in optimizing the getting the generated images correct, but this is used to improve the discriminator because we have to do that as well. Next up, since we have decoded most of the network, we'll see what the image encoder here is. It takes this output, this generated image as input. So as you would have guessed, as you would have seen, we don't actually need it for the generation process, but we do need it for the proposed loss. This paper proposes a loss, DAMSM. We'll get into that later, but it is required for that. So this image encoder takes in images, need not be the generated images, they can be the actual images as well, any image which can be basically encoded. So any image. Okay, so this can be any standard convolutional network. In this particular case, they use Inception v3 pre-trained on ImageNet, and they get both local features as well as global features. They get the local features as the output volume from the mixed 6E layer, which has this precise dimensions, and they basically mean that it has 289 subregions. You use this as your count of subregions, the number of columns, and then you grab the global features from the last average pool right before the softmax layer, and that has a vector of size 2048. So now you have both local features and global features for the image as well, and you already had those for the text. So let's get into the final part of this network, which is the deep attentional multimodal similarity model. Try saying that 5 times fast. So that is, we will call it DAMSM. Let's get into what it is. So this DAMSM tries to answer this particular question. Does the generated image actually follow the description? So the generator may have learned to generate crisp images, but it may not have learned to actually follow the description, but we want that to happen. So we want to take care of this as well. So we do that with multiple steps, many steps actually. So let's get to the first step. So over here we convert the image features, the F and F bar. Again the notation follows. This is for global, this is for local, and you convert them using just a linear layer, and you have these variables with the dimensions listed here. So this again has been brought down to a dimension which is similar to the text encoders dimension. So like word features have this dimension. They have done this intentionally so that you can directly combine them using just this, the simple dot product. So you combine these word level features with the image local features, and you have an output of this dimension. So you basically have for T words you have T rows, and 289 subregions you have 289 columns. So that is your similarity matrix. Now from experiments they found out that normalizing this gives better results, so they normalize this entire thing, and the bar here is not to be confused with the global thing. This is the only place they violate their own notation. So this S bar still means word level information, but just the normalized form of it. Okay, now the fourth step is calculating or computing region context vectors. So this is different, even though the formula may look similar, this is different from the word context vector which we saw previously, and a way to intuitively understand this was, at that time we were interested in generating the image, so we wanted to look at all the words and paint one particular subregion. Over here we are trying to find out if this word actually had any significance in painting a particular image or not. So here we do the reverse process. We look at all the subregions and for one word at a time, and we do this basically for all the words. So you see the summation, this is for all the 289 subregions, and this is the normalized score we just saw in the previous slide. This is just an attention scaling factor that they have used, and this is basically the alignment score for that. And then you multiply it with image features. Over there it was word features, here it's image features. So you have the CI, and you'll have the CI for all the T words basically. Next, we calculate the word level relevance using the ith word and formulating it using cosine similarity. So as you can see here, this is simple cosine formula which uses the current word's region context vector and the word level features. So you have them both dot product together and you have them divided by their magnitude, which is just the cosine similarity. So you have this R of CIEI. This is basically a score for each of those words on how important they are in generating the actual image. So you will have T of those RCIs and we'll use them later on. So far we have been talking only about like sub-regions and word levels, but what we actually care about is seeing whether this entire description matches with the entire image or not. So we'll now look at the global level or the image and description level. So we define image as Q and the description as D. The word level features are used here to calculate that final global level score or the image description pair score, and that can be done in two ways. So first is by using word level features, which uses all the formulas which we have seen so far. And so this is the similarity score which we just saw, and it is summed up T times for all the T words, and it is formulated in this manner to get a final score for a pair of image and caption or image and description. Again here this hyperparameter is used and it signifies the word to region context vector's importance. So you have this region context vector and its corresponding words, and you want to signify their importance, which you do by tweaking this hyperparameter. Next, you have sentence level features, because word level features are obviously more detailed than the sentence level features, but using them definitely won't hurt our process of computing the loss, so they do that as well. So as you see the bars over here, this is the complete image global features, and these are the global sentence features or the sentence vector basically. And you have just a simple cosine similarity between these two to get your final sentence level score. So now we have two scores, one on the word level scale and one on the sentence level scale, and since we'll use them later on, let's label them as 1 and 2 in red. Moving on, so we in the training process is a bit tricky, where you can't compute this DAMSM DAMSM loss for just one pair, because you need to have the global sense of how it differs from other. If it is aligned from the current pair, we also need to check how it is different from the other pairs. So you have multiple descriptions and multiple images. You basically have a number of them, capital M precisely. So you need to see what is the posterior probability of this description DI matching with image QI. So the first formulation here is, given an image, how likely is it that this particular description will be grabbed or selected basically out of the repository of all the descriptions you have. So this is just a softmax formulation, again a hyperparameter which is just a smoothing function, does the job of smoothing. Next, we want to do the reverse as well, the where you have condition, where you have been given a description and you want to retrieve an image. So you see we are doing this two-way process where you see that both of them agree with each other, and this is what we want in our text to image model. So over here the only difference is, as you can see, we have this QJ looping over here, so we'll go over all the images, all the M images in this batch, and over here we'll go over all the M descriptions of the batch. This is just a smoothing factor. Again, since we'll use those, we'll label them as 1 and 2 in blue. Finally, the DAMSM loss, the loss that they have proposed and for which we have been studying the formulas so far. So it has 4 components, and we'll get into what those 4 components means. The first one, using the definitions 1 and 1. So if you remember, this is word level features, and this one is for getting a description given an image as input, retrieving a description given an input, image input. Yeah, so you get that component. So this basically means that you have word level information and you want to get a description, select a description based on a given image. If you use the combination of 1 and 2, you get LW2, which means word level information, but given a description we want to retrieve an image. This uses sentence level information, and this is again the P of DI given QI, so description given image, and this is the reverse. So you have these 4 components, LW1, LW2, LS1, LS2, and you basically sum them up to get your final damn-sum loss. Now, since you have posterior probabilities over here, you usual way of going about it is using log loss. So for P of DI given QI, you have this loss basically, so this is the right hand side of each of these. The definitions vary because P uses the formula for similarity which we saw, and we can have that formula change based on these definitions. That's why these are different even though the formulas look same, because these definitions are changing. So yeah, so this is for P DI given QI and P of QI given DI. So yeah. That's it, that's the log loss. So you have final damn-sum loss. Now we want to have a final complete loss for the entire network. By the way, if you would have noticed, this damn-sum does not actually depend on the generated image. The image encoder does take an image as input, but it need not be the generated image. So this can actually be separately trained. So you can have your COCO dataset or your CUP dataset loaded, and you can first train this network on those real image and caption pairs, and you have this nice network trained which will give you meaningful similarity scores for when you are generating images. So this is a pretty nice thing, neat thing. Yeah. Finally, the loss for the entire network. So you have your generator loss to consider, generator losses to consider, and you have your damn-sum loss, and that is formulated in this simple manner where this is a summation as we saw previously plus lambda times L damn-sum. So this is just to control the effect of the damn-sum part of the entire thing, and this turns out to be a pretty important hyperparameter as we'll see. Okay, now that we are done with the architecture, let's move on to the experiments that they have conducted, and first we'll look at the data sets. So this is the Caltech UCSD birds dataset or CUP dataset, and here is a sample. You have this bird image and you have these nice long descriptions. Yeah, that's about it. That's it for the data set. So this is an object specific data set, and even though the ultimate goal or the holy grail of this line of research would be to have any kind of image being generated, we start small and we see the improvements on these kind of object specific data set, and then we move on to higher scene level data sets. Next, they have also conducted experiments on COCO data set. So one of the samples here, as you can see, man in black shirt playing guitar, and the other one over here. So yeah, these are the 2 data sets that they have conducted experiment on. One thing you would notice here is that this data set has longer descriptions and it has more number of descriptions. As you see here, there are 10 captions per image, so there is a richer variety that you can variation that you can get in terms of sentence, but limited in terms of image. So you would expect your images to be more beautiful in this case and a bit mediocre in this, where you have shorter captions and fewer captions per image. Okay. Moving on to evaluation. So they use 2 metrics, inception score and R precision. Inception score is the usual one in your adversarial settings, so won't explain that. R precision, they have used this in this paper only, like the other papers have not, more or less have not used the R precision, so I'll describe what it is briefly over here. So you have an image and you have a text, and you have lots of pairs of them. So you encode them using your image encoder or your text encoder, just the CNN or LSTM, and then for each of them you calculate the cosine similarity. So as we saw previously, all the formulas to get the similarity, you do that for all the encoded pairs. So you have, if you have 100 samples and 100 images, you do this with all the pairs, not just the matching pairs, you do this with all of them. And now you rank those similarities. So these have some scalar values and you rank all of them, and out of them you select the top R. This R is selected, this hyperparameter. So from those top R, you actually find out n correct pairs. So all of them won't be the correct pair. So if you have a similarity score which is high, but the caption and image are not actually related, that's bad. So you want your R precision to be high and this number n to be high. And your final R precision is n upon R. That's it for the R precision. Next, we do component analysis, and the two components that they have put under test are the most important ones, the ones that they have proposed, which is the DAMSUM part, and this is the aim, which as we have talked about, and the attentional GAN part. Whereas, whereby when you are using attention, you hope to have a better image at each generator stage. Otherwise, just an upsampled version of the previous image won't cut it. So you need to have additional details being learned at each stage, and they put this to test. So this confusing notation ATTN GAN 1 basically means that in the entire architecture they stopped after the 128 by 128 stage. So using just attention once, and ATTN GAN 2, as you will see, is the entire architecture which we discussed. So the output would be 256 by 256 images. So these are the two networks or the models that they have used, and they are controlling the lambda here, changing the lambda from the final loss function to control the effect of DAMSUM. So first off, we have no DAMSUM score, and these are the inception scores. Let's compare them by adding the DAMSUM component. So you set your lambda to 0.1, and you see both inception score as well as R precision. So this is roughly a metric of how crisp the image is, and this is roughly a metric of how relevant how similar the caption and images actually are. So you see both of them increasing, which means the DAMSUM and attention goes hand in hand to improve the image. Next, you increase the lambda, and you see that you have a good effect on the inception score as well as R precision. Over here, you would see that increasing the lambda after some point led to a bit of decrease in the inception score, but the R precision still goes high. So they use this first model, ATTN GAN 1, to do this hyperparameter search and select the best lambda value to move on to the second attention one. So over here you see this final 256 by 256 images with lambda set to 5, and you have the highest inception score as well as R precision, which is what is desired. So all of these experiments were on CUP dataset. They have only shown one for the COCO dataset in this table, and that is it. This one. So lambda equals to 50. That is surprisingly high effect of DAMSUM you want to have here, and their explanation for this is, as the scenes get more complex, you would want them to be aligned even more. So you need your DAMSUM component to be more important relatively more important in the final loss, and this is done on COCO dataset, and these are the values that they have obtained. So now this component analysis again visualized during the training procedure as the training progresses in the number of epochs. We'll see first for the CUP dataset. These are the inception scores which are rising, and as you can see, ATTN GAN 2 is over here at the top, close to ATTN 1. But as you can see, many of these models have high inception score. But what's to notice here is that particularly this gray line here, which is ATTN GAN 1 lambda 1, even though it has high inception score, it has mediocre R precision, which hints that even though this model has learned to generate crisp images, those are not actually very relevant to the description. So you want to have both of these in mind when you are evaluating your model. The same thing for COCO dataset. It is more of the same results where you have R precisions and inception scores, and both of them increase with the effect of lambda and having more attention stages. Next up, we have qualitative evaluations. This is done on inception score because that is sort of the only common metric that the other papers have used, so there's no point in doing R precision here. So inception score on both the data set. This is the first model that we discussed, and these are the values. This is the second improvement. All of the columns you see here we have discussed briefly. StackGAN, again some improvement. StackGAN V2, some improvement on some, actually they do it on the flowers and birds dataset, so you don't have value for COCO here. And PPGN, plug and play generative networks, even though they were not designed to solve this T2I problem, they did it on COCO for that for the text to image problem, and this is the output they get. And this is the ATTN GAN. These are the ATTN GAN scores, and you see them outperforming by a huge margin in COCO particularly. Next up, qualitative evaluation. So in qualitative evaluation, whenever you see attention papers, you see this nice maps where you have like sort of a heat map on which area this image is, like this word is concentrating. So we would like to briefly understand how we get these kind of images. So first, in FATTN, if you remember the beta values there, for all the words they sum up to 1, meaning you have a total attention of 1 given that you have all the words. So they do this sort of processing to make this to suppress the less relevant words, whereby if you have t words, this 1 by t is basically the mean of that. So if you have values for this attention alignment lower than that, you set them to 0, otherwise you keep them as it is. So this is just to make it a bit sparser. This is your beta cap JI, which means for one sub-region and one word at a time. So you would have for all the sub-regions and for all the words. Next, so we do this for all the sub-regions, as you can see here, 0, 1 till n-1. So for all the sub-regions, a particular word, you have all the sub-regions and you reshape that. So these are n scalar values and you reshape them to a root n by root n region. So if you have 289 features, just 17. So you have a 17 by 17 image patch, and then you keep upsampling it to match the image resolution by using Gaussian filters. So you see the most attentive region might be somewhere here, and it is Gaussian sample, like they have used Gaussian filters to get this smooth curve of attention where it is most focusing on this particular word. So you will do this you can do this for all the words, but for visualization they have used the top 5 attended words. So this I varies from 0 to 4. So basically, like, they do it for all the words, but they show only the top 5. So now let's see those generated results. This is the caption. The bird has a yellow crown and a black eye ring that is round. So this is the output of G0. Which, as you can see, it has got more or less the colors right. This sort of looks like a bird, but it lacks the details. This is the output of G1, where you have more details, where you have like clear boundaries, but still it is not good enough. And this is where you can like clearly see the eye and the bird is not blind. This is the output, the 256 by 256 output of your G2. Next. So at this stage, since the first stage did not have any attention, we don't have any attention maps. The second stage, the attention used there, so these are the top 5 beta values we saw in the previous slide. So these are the top 5 attended words. So these integers here just mean the index from this sentence, so that is not actually relevant to this problem at hand, so don't get confused by them. So the top attended word is bird, and as you can see, it is highlighted most of the bird, which is where the image generation or colorization happens, and it has basically these kind of top attended words. Next, for this stage, you have top 5 attended words, which are not exactly the same. So it means that this stage has learned to focus on some other words which it thinks that are more important, and as you can see, it has captured the words yellow and black and round, which are rather more important. So then let's say the and is. So as you can see here, this black one, because it chose black as it's one of the highly attended words, it was able to paint this thing precisely. So that is the effect you want to have as you add your attention stages. Next, another sample with this caption. This is the output of G0, then G1 and G2. These are the output for the second stage generators here, and these are the top 5 attended, like the same thing. Basically, over here, as you can see, more relevant words are captured: black, green, white. There are some useless words as well, but they are still like far below. They are not the top attended word. Next, moving on to the COCO dataset. This is the caption: a photo of homemade swirly pasta with broccoli, carrots and onions. So this is the output of first stage generator, which basically looks like, well, something you would not want to put in your stomach. This is the next stage, which gets the colors more right and crisp edges, and this one has the most clear or most precise colors. It still does not look like what the description was, but it has got the colors right, and we'll see the attention maps in a moment. So here the top attended word is which is just garbage, which is useless actually in actually generating the image. And we see this as a recurring problem with those scene level images where there is still room for improvement, where you can have actually relevant words describe this. Next, in the second stage, you can see broccoli, pasta, and like carrot have taken most of the top 5 words, swirly, so these are more relevant words. And the same thing over here, so basically useless image, a bit more clear, a bit more clear. And again, you have as the top attended word, which is not desirable, but still it is. Next, this is a particularly interesting experiment in which they change the most attended words. So basically when you have a caption like this bird has wings that are black and has a white belly. So these are the generated samples from this just a single caption. So over here, the top 2 attended words were black and white, and they changed these in this experiment to red and yellow to see how this affects the generated images. And this is the variation they get. So as you see, only changing the top 2 attended words had a significant impact on the images that were being generated. It means that the image is actually using those attended words to generate the image. The same thing again, replaced with blue and red, and these are the output images, which is beautiful. Novel scenarios. So these actually mean the captions that are not likely to happen in real world, and you want to just mess with the system as humans do, and you want to see what images they get. So a fluffy black cat floating on top of a lake got the colors or textures right for the lake and the general color for cat, but lacks enough details. So this is more of the same for the entire experiment. You can have a look at them if you want. Okay, now some failure cases. The one big particular mode of failure here is that the model is not able to capture the global coherent structure, which basically means even if you have crisp images or sort of crisp images, you would have a bird with 2 heads, which is not desirable. Or you would have a bird with 2 beaks or no heads or a small head or something like that. So these also have room for improvement. That's it. Thank you.
Okay, very good.